So thank you very much. So and thanks for the introduction. It's a pleasure to be here and to present a work on quantum search on the internet. This is the short title. This work has been done in collaboration with several people. Partly, so this is in particular Jonas Malmi, and I have here actually the picture of the senior researchers of Algorithmic, which is my startup, because this is a project that was done in between university and startup world, although it is a completely scientific and academic type of research. So Jonas, who is here, is the main author, and then Guillermo Garcia Perez and Matteo Rossi were co-authors with me of this work. The archive, the preprint number is this one, and again, the full title of the presentation is what you said. So spatial search, I will talk about spatial search by continuous time quantum walk, and in particular, differently from what is generally done when one studies search problems, I will consider a search on a topology of a network which is different, so it belongs to so-called real networks, and I will explain not before, but in the following, why we decided to do so. Of course, what I have to do to begin with is just say a few words, and this will be the outline of my introduction about spatial search, in particular continuous time quantum walks, which I use to do this spatial search, and then I will try to explain what it means renormalized in this case. What do we have to renormalize in the context of a network in particular, and the specific example I consider, which is just an example, as a matter of fact, as I will explain. We use the internet autonomous system networks, but in fact, the results are applicable to any real networks per se. And why is this type of research interesting? This is again something that is very speculative. Obviously, it is in the framework of understanding examples of what quantum computers are good for, and we do know that spatial search provides quantum advantage. It was known until now for certain graph topologies, and we wanted to push this further. And in particular, we wanted to ask the question, how do we study this type of problems? And when I think in terms of spatial search, it will be clearer in the following. I will also mean problems that have to do in general with transport, in this case, single excitation transport on a network. And what is, on the other hand, the choice of the real network is related to the fact that it has been now known since decades with the growth of complex network science, that real systems of very different type, biological systems, communication systems, social networks, are characterized by very non-trivial feature, topological feature, that they share, they have in common, despite the fact that they are of different nature, really. And of course, the question we want to ask is spatial search on real networks optimal? Does it lead to quadratic speed up, as it is the case, for example, for complete graphs and other type of networks? So again, if I can start with something more speculative, in a way you can then let your mind wander and think in terms of possible connection, especially with the background in mind that could be quantum biology, between quantum and anything which has to do with the speed up or advantage due to quantum effects, and emergence, which is a property typical of complex networks in general. And therefore, you can ask questions if you properly think of addressing this type of framework that I will present. In the future, you can think of addressing questions like, are quantum properties of relevant in the emergence of complex network topologies? Can they be useful? If you think in terms of biological networks, have they play a functional role in the growth of biological complex systems, and so on and so forth. So I'm not saying that I'm answering to any of these questions, but I think that the framework I will be presenting could be useful to start addressing some of these questions. And of course, when we think in terms of speed up or advantage with respect to a classical algorithm, we are thinking obviously in terms of the scaling. So what we are, in the case of Grover search, which is in particular an instance of a search on a unstructured database, or spatial search, which is the analog for the structured database. What we are looking at the time of the protocol and how it scales with respect to the number of items in the database, which in this case is equivalent to the number of nodes in the graphs. And we know that the scaling for the quantum algorithm, again, for regular lattices and for certain graph topologies is of order square root of n, which is a quadratic advantage with respect to the linear scaling that we observe in classical algorithms. And now, if you think in terms of what are the type of real systems that one can start investigating, I'm referring to a number of examples here, not necessarily this one. It could be protein-protein interaction, biological networks, protein-DNA interactions. I will talk about the internet, but any real network, because they all share the same topology. So what I'm saying is going to apply also to these other types of networks. However, the main issue here is that real networks, what we have, are really taken from databases, and they are single instances. So how do I study scaling if I have an instance of the network? Like in the case of the internet, I have one real network with a fixed value of n. How do I study scaling? How do I predict, for example, the future behavior in general? And here is actually what we, I think what for me was the most interesting, or is the most interesting part of the results that I will be showing you. But I will begin by very briefly recalling the main properties of spatial search by continuous time quantum walk. I will then talk about the idea of introducing this scaling. Actually is through a complex network science result that introduces geometric embeddings and renormalizations, so scaling, and through which I will introduce this concept of replicas, statistically equivalent replicas of the original network. And then I will show you the results, and in particular, I will discuss about the optimality of the spatial search on a real network, which is the internet. But let me begin by briefly recalling a few key messages about the spatial search. The spatial search algorithm. So spatial search is a generalization of Grover's algorithms, where the spatial structure of a connected database is taken into account. And in our case, the structure is encoded in the topology of the network, in this case, so therefore it's a real network. And we consider continuous time quantum walks, which are basically the quantum analogs of the continuous time classical random walks, or if you want, the continuous limit of the discrete quantum walks. And basically, you can imagine them as describing the propagation of a single excitation, in this case over a discrete set of positions that are identified by the nodes of the network. In a seminal paper by Childs and Goldstones, it was shown that spatial search based on continuous time quantum walk can solve the spatial search problem in certain regular graphs with quadratic speed up with respect to the best classical algorithms. And it was extended, the results, initial results of Childs of Goldstone was then extended, and nowadays we know that this algorithm is optimal for graph topologies which include star graphs, graphs with broken link, fractal graph, random graphs, 1D graphs with long-range interactions, and so on and so forth. However, general conditions for the graph to be efficiently searchable are not known. So how do we generally implement a continuous time quantum walk on a graph? First of all, I introduce the notation. I indicate a network with the ensemble, with the set of V, where V is equal in our case to n, indicates the number of nodes, and E are the edges or links. And I will introduce this quantity that will be very important in describing the dynamics and the characterization the topology of the networks. It's called the adjacency matrix, and basically is composed of 1 or 0. I have a 1 when there is a link between node J and K, and 0 otherwise. I will introduce the degree of a node that is mathematically defined in this way, and it's simply the number of links incidents to the node. And then I will introduce the Laplacian, which is just given by the D is the matrix of the having in the diagonal the degrees of each node, and A is the adjacency matrix. So L is just D minus A. So this is just notation, to set the notation at the beginning. And then the idea is to find, so the idea of the algorithm is to find a node W. So W, I will indicate with W one of the nodes of the internet, and I will define, will associate a Hilbert space which is spanned by vectors 1n, again n is the number of nodes overall, and then the Hamiltonian that is considered in general when studying spatial search is an Hamiltonian that consists of two terms. The first term is a Laplacian, and here gamma is a constant that I will describe in a moment, and the second term is the oracle Hamiltonian, which is the projector on the nodes we are looking for. This constant here, gamma, regulates the flow of probability amplitude per unit time between the nodes. And so I will, of course, in the following, I will fix certain parameters, but of course I will have to optimize over these parameters. I will explain it in a moment. But this is very simple Hamiltonian, and then you have an initial state to be prepared. And generally in spatial search or in search, continuous time quantum walk with the spatial search, one prepares as initial state an equally balanced superposition of all the nodes in the network, and then just evolves. So then there is a evolution driven by the Hamiltonian. And finally, this is okay. Importantly, as a very first step, we are not considering here any effect of noise, but clearly it's interesting to consider then in case in which nodes are present, how they can sorry, in case in which noise is present. For example, it could be by randomly eliminating some of the links or other forms, or adding one of the noise. There are several models, but we are not considering here. So the dynamics is just unitary at this stage. And finally, we want to study, we introduce and we look at the probability PW, that is the probability of success. Remember, W is the target state, psi of t is the evolved state, and generally the spatial search is successful for a certain time. At a certain time, the probability of measuring the quantum work at the position of node W is close to 1. And in particular, obviously, this means that the probability of success will have to be obtained by maximizing over first of all, the parameter gamma that I introduced, or optimizing over gamma, not maximizing, but finding the optimal value of gamma, which leads to the maximum success probability, and also finding the minimum time for which the probability is close to 1. So this is defined the optimality condition. So if the probability of success is order 1 in a time t equal to square root of the order of which scales, sorry, as square root of n, then I can claim that the search is optimal. Okay, now this is a very brief review of the main ingredients related to spatial search and then the dynamics that I will be considering. And now I will introduce the tool that we use to study scaling. And this is leads me to the introduction of network geometry, and in particular I have to say something in general about properties of real world networks. So we know that despite their complexity, real-world networks that can belong to different domains, as I mentioned before, they share certain properties. For example, the degree is heterogeneous. This means that basically the so-called power law distribution of the degrees is present. So the majority of the nodes have very low degrees. They have very few connections, and there are very few nodes instead which are hubs, so they present many connections in the network. They exhibit clustering, which is really the presence of triangles in the topology of the network, and they exhibit the small world property, and that is related to the fact that each nodes can be connected to other nodes with very few links looking at the shortest path. in the network. But the origin, so since when network science was started, a number of models that reproduced degree heterogeneity or small worlds were presented. These are properties, by the way, that are very different with respect to random graphs, but they emerge in each of these real network. But the origin of clustering really remained elusive for a very long time. So there were no models that could generate graphs that would clearly explain the origin of clustering. And the best models that explain this property are so-called geometric models. So geometric models are really a framework for which clustering emerges somehow, or is related, or is a reflection of similarity between the nodes. I will just briefly recall these results, but I will not go into the details of these results. But for example, in the internet, the similarity space is congruent with geographic distance, and therefore paradigmatic. This is actually not only the case of the internet. So in the paradigmatic network geometric models, the similarity space is really represented in terms of an underlying metric space. So what was realized, that there was really a possibility of observing these complex networks in terms of really like building maps, creating or identifying an underlying geometry, which very often is hyperbolic geometry, hyperbolic space, and in a way mapping them into this geometry, and then really noticing how distances emerged and how certain properties that I will show soon are reflected into these geometric embeddings. It will become clearer once I present the first examples. These models or these geometric approaches enable the so-called embedding of the network. So one finds the coordinates of the nodes of a real network in this abstract similarity space. And it was proven that this, for example, allowed to navigate the network efficiently. So there are several interesting, or even to describe, so to identify communities within the network in a very natural and more, let's say, more small scale manner. And then finally, what is interesting for us is that so that real world graphs, once embedded in this geometric space, are found to be self-similar. And this is with respect to our coarse graining, transformation, and similarity spaces I will introduce in a moment. Again, only visually. The math is actually quite complicated on how to do this renormalization. But what is important is that recognizing or noticing this self-similarity allows to introduce transformation very similar to renormalization groups, really, but adapted, of course, to the topology of real networks. And this allows in terms to reproduce or to create smaller scales replicas of the real networks, which very importantly have very similar topological properties with respect to the original networks. Now, the paper that discovered this existence of self-similarity in real networks is this paper by Guille, which is actually one of the co-authors of our paper, Marianne Bogugna and Mariangel Serrano. And all the details are explaining in the paper, and I really will not have time to describe them in detail, but basically what you do in the renormalization, here with L, I indicate the different layers, so the different replicas of different levels of renormalization. And this renormalization is only performed after the network is embedded in a certain metric space. And then nodes are combined together to create these super nodes. So this is how the replicas are created. There are mathematical formulas that describe all this, and I will not go into these details. The only important points I want to make is that the geometric embedding is done, and we will see it in the next plots, in hyperbolic space, and the smaller replicas with same topological properties, they share the same dynamics, and they share the same statistical properties. Okay, so I can study any of these replicas, and I know that the dynamics will be and the statistical properties will be the same in all the layers. due to the self-similarity. And okay, now I have all the basic ingredients to start studying the spatial search on the complex network, in particular to start studying the scalings, because I will build first these statistically equivalent replicas, and then in this way I will have a practical manner to see how the spatial search of the dynamics really performs as I vary the number of nodes. So in particular, I'm going to study. This is just an example of the layers that I'm considering from 1 to 5 with the corresponding numbers of nodes and edges. Again, these are replicas of a snapshot of the internet network at the level of autonomous system, which was taken in 2009. In these, I will now show you a plot. I will describe it, but for now I just want you to focus on not on the color. I will tell you what the color is. I just want you to focus on let's say the geometries and the topologies of these networks, which again is replicas of the internet network in different degrees, different flows of renormalization, 1, 3, and 5. Again, I defined here what they are. And the first thing that I would like you to notice is that usually this is by definition of the embeddings. When you do these representations, immediately the radial coordinate becomes associated to the degree. So this is the way really in which they are constructed. So the majority of the nodes are here at the periphery, and they are all nodes of low degree, while the hubs, the highly connected nodes, are in the center. Okay, so again, this is the structure itself of the network. And remember, because I mentioned about the degree heterogeneity as one of the properties of complex networks, and in particular, you will see from here that the majority of the nodes are indeed the low degrees nodes, and they stay in this part here of the network. Okay, and now we start with the spatial search. We start with the dynamics, and we prepare an initial state. We start the evolution, and we calculate the probabilities, and we optimize them. By calculating again the probability of success and optimizing over the parameters gamma. So finding the value of gamma, which gives the optimal probability, and calculating the minimum time. And of course, these are the parameters to optimize. In the future, in the last part of the results, I will also introduce this TW, which is equal to T divided by the probability of success, and takes into account the fact that in some cases the probability of success is not really very close to 1, and therefore I actually have to repeat the algorithm several times to obtain significant results. So I have to rescale over the probability of success. And the first result I want to show you is a result in which here you see the value. So we can extract from this study the value of gamma for which which leads to optimality, so for which the algorithm is the best. Interestingly, this value of gamma is related to the degree, and in particular is 1 over the degree of the nodes. So you see all these dots are really related to each. So I'm changing now in this plot the target by covering all the nodes in the real network. So and so the dots are related to the choice of different targets of the search, and you see that there is this behavior for which the gamma optimal depends clearly on k, and is like 1 over k in particular in this case. So we know already what is the gamma optimal from this study, depending on the target that we choose. And if you look at this probability as this quantity TW, we see that for low degree there is no clear correlations emerging with respect to TW, but for high degree nodes, again, there is a behavior which shows correlation between TW and the degree of the node. Now, all these results combined together will allow me to introduce first the probability of success and finally the scaling, which is the last thing I want to talk about. So when it comes to the probability of success, this is the same plot as before, but now I'm visualizing with color the probability of success depending on the node chosen as target. Okay, so if I choose here this node, one of the yellow nodes, this is a hub, as a target, the probability of success actually is very low, while the low degree nodes have very high probability of success. So when you run a spatial search on the internet, the first thing you notice on a real graph, as a matter of fact, is that there is immediately a difference in whether you choose as a target state a hub or a node or a low degree node. And finally, so we go towards the scaling, and this is, by the way, why it is not something that we are immediately understanding. Okay, so this is something we have some ideas about, but we don't have a clear understanding of why there is this distinction which immediately emerges in the transport, in the dynamics, really, and in this case in the probability of success between hubs and low degree nodes. And finally, the scaling. So here I'm plotting the time. So first of all, the first thing I do is now I'm not considering for the scaling anymore a specific node W, but I'm averaging over all the nodes. Okay, so that's why you see only individual points, and I'm comparing the results. So forget about these lines for now. I will not explain them. It's a comparison with an approximation which is known from the literature. But here the blue triangles are related to the search algorithm on the internet, and we compare them with the two different models of different models of networks very well known. One is the random Erdos-Renyi network, and the other one is the Barabasi-Albert network. So it's just a comparison between other categories of networks, just to compare with real networks. And here we see that if we look at the time, you will see that the classical, again, by comparison, the classical is this green line here, that is the linear scaling, while quantum, for all the cases, for all the networks, both the real networks and the Erdos-Renyi and Barabasi-Albert, present a scaling which is very close to optimal, is not optimal. Okay, so you have it follows really the square root of n behavior. But now if we look at the quantity that instead is more relevant for us, which is TW, which is the case in which we are actually taking into account the fact that sometimes we don't have good probability of success and therefore we need to repeat more than once, you will see that actually now differences started to emerge. And you see here that actually while the behavior is, so the scaling itself seems better than the classical one, it is not optimal anymore. However, if one looks, or if this is because we are adding the results for the hubs, which are very bad. So if one excludes as targets of the search the hubs, then which constitute, by the way, because of the properties of the networks, something like 10% of the nodes of the networks, we will go back to optimal scaling. Okay, so it really depends on whether or not you want to identify with your target the hub or the low degree nodes. So takeaway messages. The first one is that, so for me, one of the things that was more interesting in this result, independently from the analysis of the, of the spatial search per se, is that when we want to study transport on real networks of different types, because we need actually to study scaling, then using these renormalized replicas can be very interesting. It allows really to have at your hands a very interesting tool. Interestingly, I only mentioned the paper in which the renormalization, let's say the coarse graining is presented. However, the inverse process, so there's another paper by the same authors published recently in, I think, PNAS, in which they show how actually the inverse property, which is more complex, obviously, allows to, so can be presented and can be offered, and you can also guarantee that the dynamics on the larger networks are the dynamical properties like diffusion of the larger networks are preserved. And this obviously allows to study dynamics of real networks or make predictions in the dynamic of the real networks. And then we noticed how spatial search on quantum real networks is almost optimal. Unfortunately, the hubs contribute to lower this optimality when they are taken into account, if one of the nodes is the hub. And the difference in the probability of success between hubs and low-degree nodes is something which emerges empirically. Future questions, how can we reach optimality? Can we do it by preparing a different initial state? So why are we preparing an equally balanced superposition? In fact, when normally this is done for I don't know, complete graphs just because of symmetry, but here the topology is different. So maybe there are other different initial states which are not so symmetric and that could lead to optimality, also taking into account the hubs. Then obviously it would be interesting, as I said before, to study what is the effect of the noise. And in general, independently from search, one could use this framework to study, or this method to study transport in biological networks and how these behave as the network evolves. So has more and more, a larger and larger number of nodes N. And this is everything I want to talk with you about. And thanks a lot for listening. And I'm happy to answer questions.
Yeah, thank you very much, Sabrina, for this nice talk. So I hope it has hit some resonance, as I used to say this morning, and therefore the paper is open for questions. So, are there any questions? Is everything so clear that...
Yeah, hello, this is Susanna. I'm just trying to switch on the video, if I manage.
Yep.
Yeah. Wait.
Yep.
Hi, Sabrina, many thanks for the nice talk. I just have a curiosity, actually, when you mentioned the biological networks and mentioned proteins. What sort of situations do you have in mind, and what is, let's say, the state of the art at the moment concerning the modeling of protein-protein interactions using this framework of complex networks?
Yes, yes, Susanna, good point. Of course, when it comes to protein-protein interaction, we are not, and we cannot claim that protein-protein interaction networks are quantum. So in a way, certainly I'm not mentioning that this would be a good way of studying spatial search on protein-protein interaction networks because they are quantum. However, something interesting, so we have recently studied something related but interesting that is more in the framework of quantum-inspired algorithms. So if you look at continuous time quantum walks as a way of studying diffusion processes, in particular for protein-protein interaction networks, classically, this is one of the ways of doing something that is known as a link prediction. So to predict whether likely there will be a link in the protein-protein interaction networks, which is not experimentally revealed. If you think about the protein-protein interaction networks, the majority is very, I think that it was estimated that only 30% of the interactions are known. The majority is really not known. So, and generally people use, for example, random walk with restart. There are algorithms that are used to predict the links, so-called link prediction thing. And apparently, if you use instead a continuous time quantum walk, in some cases you actually have a better performance in the link prediction with respect to the classical method. Again, these are heuristic things, but just to say that sometimes, and you run it on a classical computer, so it's not in this sense I talk about quantum inspired, but you can still have a process that in the end allows you to predict the links more efficiently than the classical random walk with restart. So in a way, it's again, without claiming that these networks are quantum, you can still still have a quantum-inspired algorithm that allows to make good prediction on problems which are very relevant, like, again, link prediction in this case.
Okay, perfect. Very good.
Thank you.
Yeah.
So, ciao Sabrina, thank you for being with us. Well, naive question. I know very little about this kind of research, but you mentioned this renormalization group technique.
Yes.
And well, this was developed essentially by Wilson just to study phase transitions, right?
Yes.
So my question is, do you face or expect some kind of phase transition in the network you study? And
due to the renormalization, it's an interesting question. I don't know. My answer is I don't know. For this specific type of renormalization, okay, in a way, yes. In a way, yes, of course. In a trivial way, yes. So when you renormalize, at some point, you will be, you will reach a point in which you will, if I remember correctly, in which at some point you will reach a graph, so a replica, which is complete, so a complete graph. So in a way, yes, you do have a transition in the sense that complete graph is not a real graph anymore. It's not a real network anymore, so it has different properties. I'm pretty sure that this is the case, and so you have to avoid actually to go to this limit. So this is a limit in which this renormalization flow does not work anymore. But I think I remember that this is one of the consequences, because of course you're combining nodes, and therefore there is you have to stop the flow. If you want to have statistically equivalent networks, you have to stop the flow so for as long as this can still be considered a real network. Yeah, yes. Okay, but it's a trivial phase transition, I don't know. But it's in general is interesting, yes.
Okay, thank you.
Perfect. There was another question by Anna Sampra.
Thank you. Yeah. Hi, Sabrina. Nice talk. I also don't know anything about that, but I was curious. Can you explain a little bit more these differences that you find in the probability of success between these hubs and these low connected? Because for me, it sounds kind of counterintuitive, but yes. I don't know.
Yes, yes. Well, actually, I think, so the only way in which we can, we sort of understood it, we don't have a physical intuition of why it is so. We sort of understand it in terms of that part. So in terms of the fact that in a way, so in terms of the spectral properties of the graph, really, and I don't have ways of explaining it in a way that is simple other than mathematical. So when you consider the eigenvalues and eigenvectors of the graph, it is so, and you consider the dynamics, and you sort of let's say, if you would have a complete graph, what would happen in spatial search is that you would have one of the, so to say, the initial state is this is the equally balanced superposition, and the first excited state would be the target state, and then you would be oscillating between the two, and then you would reach the probability of success when at half oscillation. Okay, so this is in the case of, it's very simple actually, the dynamic for a full fully connected complete graph. But what happens now is that actually you have some sort of probability flow in the dynamics outside these two subspaces, outside what I called S and W. And that's why you don't have optimality. And what happens is that if you look at the spectrum really of the graph, you will see that the hubs are those for which the probability flow outside this space is larger. So you lose the I don't know, dynamically, you never go back to the state W, which is the target state. But it's more of a mathematical observation, but it is not really, we don't have a physical intuition, if there would be any physical intuition, actually.
Thanks.
Yes, Sabrina, would you, from your findings, have something like, say, a rough guideline for a quantum engineer setting up an internet of how to balance the trade-off between the difficulty in optimal state preparation on the one hand side, and maybe creating something like an optimal graph, which is not the full one, but sufficiently rich that one really has a good balance between an easy to get initial state and workable, handleable type of network graph?
Yes, it's a very interesting question. So no, I don't know actually. I mean, I know that there are people who are there are many people who are studying, you know, how the quantum networks, but you know, let's say commercial quantum communication networks might evolve, because we know that you know, internet, for example, has evolved to have this structure, but it is not said that a quantum communication network would evolve to, you know, to have a topology which is similar to the real networks. This we absolutely have no idea, right? If we would don't think about engineering, but think about emergence in this case. So we don't think beforehand how it would be. So your question was more related to, can we have a guess of what would be the optimal way of
and you're perfectly right in saying a rough guess definitely would do. So I'm not asking for a full-fledged mathematical answer at this point, but maybe for some structure which serves as a good guideline.
Yes, yes. So one of the reasons why you know, this internet emerged, or real graphs emerged in this manner, is because they have this property of being resilient to noise. So breaking links in these real graphs, like in the internet, does not strongly affect the transmission. Okay, they're very resistant to link breakage, although attacking the hubs instead is very disruptive. So apparently this was something that somehow it emerged as a property, and perhaps is related to the way in which it emerged in this way. But if you ask me about a prediction, I would say that most likely what I would imagine the quantum internet would be will be not a single layer network, but a dual network, because you would have a quantum layer where you transmit the quantum information, but you will also need to have the standard communication, classical communication, which will happen over the internet, I assume. So I really I cannot give you an answer other than I don't know, but it will be more complex, and it would be dual, because in a way what you have to optimize is two types of communications, right? It's not just it's a combination of the two. So no, I don't know. Yes, it's just speculation.
Yeah. Yeah, there's another question by Domenico Pomerico.
Yes, thank you very much for your talk, Professor. I would like to ask you just some details about the mapping in the hyperbolic metric for your graphs. Why is it useful, and is there any procedure adopting also an hyperbolic metric among different scales of your graph? Is there any trial to run the search also including transitions between the scales to optimize?
But transition between the scales would mean different values of n, no? So in a way, we want to study the optimality for each value of n. So the optimality, sorry, the scaling for each n to prove the behavior of t as n grows. So we study, that's why we do the search on all the layers. So of course we study the search on all the layers to see what is the time t or TW, never mind, as n, how it scales as n increases. So in a way, I don't know exactly what you mean with the across the layers. So we are fixing the layers here, and we study t as a function of, so for each of the layers, as n changes, the number of nodes changes. And then for the first part of the question, which is related to the embedding, so the reason of the hyperbolic space is, so these original papers, they found two types of metric spaces that are useful for the embeddings, and one of them, for visualization purposes, the hyperbolic space is the best. I mean, in a way, it is highly non-trivial, and I don't even remember the formula for doing the embeddings themselves. But it is a property that it is found. So you have to, once you find the underlying hidden matrix, obviously you have to check that the statistical properties are preserved, and basically they discover the existence of this self-similarity. So whether there exists other I think I know that there exists, because it's not my field. I don't come from complex networks, but one of the co-authors is a complex network theories. I think I believe that they also embed in different, so not necessarily in two-dimensional spaces. They can do embedding, geometric embeddings, as I'm sure, in many dimensions. Only that they always use the minimal number just for simplicity. But you can also have embeddings in actually in D dimension. So the same theory, and I think I was actually talking with one of the authors yesterday, and she mentioned, Mariangel Serrano, she was mentioning that they study the self-similarity also for D dimensions itself. So yes.
In any case, please forgive me my second part of the question, just to be clear. I mean, if you start from a fixed network, then the renormalization procedure is, let me say, automatic. So once you build on your hierarchical network with multiple layers, I was just asking you for curiosities if it could be helpful to implement the search among multiple hierarchies that you built on your starting network to implement the search.
But we do. So we do implement the search on all the layers. Is this what you say? But
not over a fixed layer. I mean, how can I say? If your particle, your evolution moves not only at a fixed layer, but
okay. You mean across the layer?
Across the layers, yes.
Okay, no, we have not done it. No, yes. But why would this be useful?
No, I don't know, but at least for one-dimensional systems, it is a common structure, the one to map the renormalization of one-dimensional system in de Sitter spacetime or anti-de Sitter spacetime for the hyperbolic metric case.
Okay. No, what we were trying to do here is to see what was the property, how the scaling, how the dynamics would perform. In this case, the search would perform if we change n. This was the only reason. It was a simpler, let's say, question. But yes, I understand now. Thank you for clarifying. Yes, it's an interesting point.
Thank you for your talk.